Hello. In today's video, we're going to be looking at vapor pressure and the equation for vapor pressure, which is called the Clausius Clapeyron equation. So, we're going to think about going from the vapor phase, or from the liquid phase into the vapor phase. So, if we take any substance at a given temperature, we can usually think about it in terms of one state. So, for instance, if we have something like ethanol. Ethanol has a boiling point of approximately 79 degrees Celsius. Okay, so if we are below that 79 degrees Celsius, so if we're at a temperature of, 70 degrees Celsius, our assumption is that that ethanol would then be in the liquid state. And then if we say, okay, we have a temperature of 85. All right, let's do 90. Again, we have an assumption, since we are above that boiling point, that our ethanol is in the gaseous phase, or gaseous state. Okay, so we generally make an assumption. If we're below the boiling point, everything is in the liquid state. If we're above the boiling point, everything's in the gas state. But that's not true. So these are not true. The assumption is incorrect. So why? Why are these assumptions incorrect? Let's remember, real quick, one of the definitions of temperature. So temperature itself, we can call that a measure of the average kinetic energy. If it's an average, that means we're going to have things that are at lower kinetic energy and things that are at higher kinetic energy. So there will be a distribution of kinetic energies at any given temperature. Okay, so we can take that whole idea of our ethanol. We can look at 70 degrees, and we can look at 80 degrees. And I'm going to put this onto a graph. So I'm going to have my 70 degrees Celsius ethanol, and I'm going to have my 90 degrees Celsius ethanol. Okay, and I'm going to look at the number of molecules at with a particular kinetic energy. Okay, so remember, so kinetic energy is increasing as we go from left to right. So here on the left side we have lower temperature, lower kinetic energy, and higher kinetic energy. Okay, so I've got 70 degree ethanol. That 70 degree ethanol is going to have a distribution of particles. Okay, the greatest distribution is up here at the top, right? And right about here is where we have enough energy. So this is where our kinetic energy is great enough to enter the vapor phase. So despite the fact that our 70 degrees or 70 degrees Celsius ethanol is below that boiling point, we still have a fraction of molecules. This fraction right here, let me get my blue. This fraction right here that has enough energy. Actually, this fraction right here that has enough energy. There we go. To go into the vapor phase. Okay, let's do that same thing for the 70 degrees, or 70 C ethanol. 70 C, we have a much larger fraction of molecules that have enough energy. So now we've got a more significant portion a larger portion of molecules that have a greater or great enough kinetic energy to enter the vapor phase. And as we increase temperature, we're going to continuously shift that kinetic energy curve. It's going to widen out and shift to more particles having enough energy to overcome the intermolecular forces that are holding it in place. So as we increase temperature, we're going to increase the fraction of molecules that can escape the vapor phase, and our increase of temperature will cause evaporation to occur more quickly. Okay, so increased temp will result in an increased fraction of molecules with enough kinetic energy to overcome intermolecular forces and escape into the vapor phase. And will therefore result in evaporation occurring more quickly. Okay. In addition, so in order to have evaporation occur, obviously we have to have enough energy. But in addition, we also have to have the molecules or particles they have to be at the surface of the liquid. Okay. So, let's think about what occurs during evaporation. Okay? So, at the very beginning, we have a liquid. Let's take a liquid and we're going to put a top on that liquid. So we've basically made what we would consider a closed container. So at the beginning, when we first put that liquid in that closed container, we are going to have the liquid particles vaporizing or evaporating, so going into the liquid phase. Okay, so the gas phase. So we're going to have our liquid particles escaping from the surface of the liquid into the gas phase. Okay, over time, as those particles interact, those vapor phase particles interact with other vapor particles in the air, they may transfer their energy to other particles, and in that case they're going to lose some energy and they're going to condensate again, or they're going to condense back down to a liquid state. Okay? Eventually, we will get to a point where we have our liquid state molecules going to the gas phase at the same rate that our gas molecules go to the liquid phase. So, the rate of evaporation equaling the rate of condensation. So if we have a closed container, we'll eventually reach a point where this will occur. Hopefully you remember, this is dynamic equilibrium. So if we take a liquid, put it in a closed container, eventually we'll reach a dynamic equilibrium between our liquid phase and our gaseous phase. And that equilibrium, that dynamic equilibrium will depend upon your temperature, right? So at lower temperatures, there's going to be a lower amount or concentration of gaseous particles. At higher temperatures, there's going to be a higher amount of gaseous particles. But as long as you maintain a specific temperature and you have a closed container, you will reach dynamic equilibrium between your gaseous phase and your liquid phase. Once you've reached that, we call the pressure exerted by the liquid our vapor pressure. So our vapor pressure of a liquid is the pressure exerted by the vapor when the liquid and vapor are in dynamic equilibrium with each other. And remember, for our liquid and vapor to be in dynamic equilibrium, they must be in a closed container. Anytime we say equilibrium, we mean dynamic equilibrium, not static equilibrium. Okay? So, must be in a closed container to reach equilibrium. If we have an open vessel, evaporation will occur until there is no more liquid left. And this has to do with Le Chatelier's principle, which we'll talk about when we get to the equilibrium chapter. But just know that if we have an open vessel, we can't have dynamic equilibrium being reached, so we would just evaporate until you no longer have any liquid. Okay? So, when we think about substances, when we think about their vapor pressures, something that has a high vapor pressure so something at room temperature that very easily evaporates, we would call that substance volatile. So perfumes are generally considered volatile. They very easily go into the gas phase, and that's why people smell nice or sometimes horrible. But those are usually volatile substances, so people can smell them. They'll easily go into the vapor phase. Okay. Now, we generally relate vapor pressure to boiling point, and the reason that we relate the two is because boiling point can be defined as the point at which our vapor pressure equals our external temperature. So that temperature, when our vapor pressure equals external pressure, that's when we are reaching a boiling point. Generally, boiling points are given at 1 atmosphere. So to say that water has a boiling point of 100 degrees Celsius, it means specifically water has a boiling point of 100 degrees Celsius at 1 atmosphere of pressure. When we change our external pressure, our atmospheric pressure, we change our boiling point. So when we're thinking about external pressure, it's the pressure exerted on our substance, right? So our external pressure or atmospheric pressure, as we increase that, it's harder for our gas to or liquid to escape into the gas phase. So an increased external pressure results in an increased boiling point because it's harder to get things into the vapor phase. So an increased external or atmospheric pressure results in an increased boiling point. So if you are on the top of a mountain, your boiling point will actually decrease, right? Because as you go up a mountain, usually pressure decreases, so boiling point will increase. Another thing that's going to affect our boiling point are going to be intermolecular forces, right? So and our vapor pressure as well. So if we have, if you think about vapor pressure is basically how easy it is to get something into the vapor phase. If you have something that has a high vapor pressure, it's something that is easy to get into the vapor phase. Something with a low vapor pressure, harder to get into the vapor phase. Something with a high vapor pressure is going to boil easily, right? So high vapor pressure, lower boiling point. Lower vapor pressure, you have to increase the energy in order to get more of your substance into the vapor phase. So low vapor pressure results in high boiling points. And then we can bring this all into intermolecular forces. So intermolecular forces tells us how hard it is to take something and separate it from other things. So if we have strong intermolecular forces, it's really hard to separate substances, right? So those intermolecular forces are holding them all together. So if we have something with strong intermolecular forces, it's going to decrease our vapor pressure because it's going to hold things in the liquid state more. Okay? And then if we decrease vapor pressure, it's harder to get things in the vapor phase, so it's harder to get to that atmospheric pressure equaling vapor pressure, or vapor pressure equaling atmospheric pressure, so that's going to increase our boiling point. So generally, non-polar substances are going to have high vapor pressures with low boiling points. Things that can hydrogen bond are going to be things that have low vapor pressure, high boiling point. So here's some substances right here. So we have carbon disulfide. We have, so this is carbon disulfide. This is methanol. This is ethanol. And then octane. Okay. So we can take these substances. So this is a nonpolar substance. This is a hydrogen bonder. This is a hydrogen bonder. And this is nonpolar. So our two hydrogen bonders are very similar, but our ethanol, this one right here, has greater dispersion forces. So they have as much hydrogen bonding because they both have one oxygen-hydrogen bond, but this ethanol at the top right has greater dispersion forces because it has a larger molecule. Okay, so if we look at our vapor pressure versus temperature for these four substances, carbon disulfide, methanol, ethanol, and heptane, as we see, our vapor pressure is going to be greatest at any given temperature for carbon disulfide because it is a weaker substance. It has, it's very small, so all it has is dispersion forces, and they're very, very weak. Then we have methanol and ethanol. They're both hydrogen bonders. Oh, I'm sorry, this is heptane. Oh, I drew octane. Close enough. These are both hydrogen bonders, the ethanol and the methanol. Methanol is smaller, so smaller dispersion forces, so we'd say it has less intermolecular forces holding it together, so it has a higher vapor pressure at lower temperatures than ethanol. And then ethanol is significantly smaller than our heptane, or actually this is hexane, the one that I drew. Close enough. So our hexane will actually, because of its large size and its high dispersion forces, will have the lowest vapor pressure at any given temperature. Okay. Some other things to note when we're looking at these vapor pressures versus temperature, which brings us into our last part of this video, is the fact that, oh, sorry, let me also go over, so here's another example of how intermolecular forces affect our boiling point. So we see here, as we have stronger intermolecular forces, we have lower vapor pressures at any given temperature. And we can translate that into boiling point, right? So higher vapor pressure, lower boiling point. So they're going to be an inverse relationship. Higher intermolecular forces, higher boiling point. Or stronger intermolecular forces, stronger or higher boiling point. So those would be directly related. And we can see that if we look at our group, any one of our groups. So going from, we can start out with group 4. So group 4 in general, since we are increasing our molecular weight, we are going to increase our intermolecular forces and result in a greater boiling point. Now, we don't see that. We see kind of a different trend right here. An interesting trend over here going on. In general, those that can hydrogen bond, which are these three right here, that will also have a fairly significant effect on the boiling point. But in general, as long as we increase our molecular weight, we're increasing our dispersion forces, as long as we don't take into account hydrogen bonding. But hydrogen bonding, if we have a substance that can hydrogen bond, it's going to cause it to have a significantly higher boiling point. So intermolecular forces are going to increase our boiling point, whether it be dispersion forces or hydrogen bonding or dipole-dipole type of things. All the rest of these substances in here are pretty low or pretty nonpolar in nature. Okay, so as we saw earlier, our vapor pressure and our temperature, if we were to plot the two of them, we see that we do not have a linear relationship. So it's a non-linear relationship between temperature and vapor pressure. So an equation was developed called the Clausius Clapeyron. which is used to relate temperature and vapor pressure. For a given compound. And it was found that if you were to take any compound and you would take the natural log of the vapor pressure and you were to plot it against the 1 over T of that vapor pressure, you would get a linear relationship. So the natural log of the pressure, vapor pressure, versus 1 over T, this gives us a linear relationship, which is what we get our Clausius Clapeyron. So ln P vap is equal to negative delta H vap over R times by 1 over T plus a constant. Okay. So P vap is our vapor pressure. Delta H vap is our enthalpy of vaporization. Oh, our vapor pressure needs to be in torr or millimeters of mercury. Our HVAP will be in joules per mole. Our R is our gas constant. But since we are dealing with energy, we are talking about 8.314 joules over moles times by Kelvin. So that gas constant. T is temperature in Kelvin. And then C is just a constant based on the liquid. Okay, so plotting that, we get a linear relationship, and that linear relationship has a slope equal to negative delta H vap over R. And then the y-intercept, let's try the right one, is going to be C. Okay. So, you guys will at some point do a lab where you're going to take a bunch of different vapor pressures and temperatures and you can plot them. But generally in this class we look at what's called the 2-point form of the Clausius Clapeyron. And that's the one that you guys are actually going to be doing calculations with. So it's ln P1 over P2 is equal to negative delta H vap over R, 1 over T1 minus 1 over T2. And you can use this to determine your enthalpy of vaporization if you have 2 pressures and 2 temperatures. Or you can figure out P1 or P2, T1 or T2 if you have the other things. Keep in mind that our temperature always needs to be in Kelvin, but our pressure can be any, as long as you keep P1 and P2 the same. Okay, and that's it for this video. Bye y'all.